Welcome to Conskill, your lifetime career partner. Tricana is a pioneer and trailblazer in the field of civil engineering and construction training, seeking to bridge the gap between engineering studies and the construction industry. Soil Consolidation Test IS 2720, Part 15, 1965. Consolidation. Consolidation of a saturated soil occurs due to expulsion of water under static, sustained load. The consolidation characteristics of soils are required to predict the magnitude and the rate of settlement. Need and scope. The test is conducted to determine settlement due to primary consolidation. Rate of consolidation under normal load. Degree of consolidation at any time. Pressure-void ratio relationship. Coefficient of consolidation at various pressures. Compression index. Need and scope. From the above information, it will be possible for us to predict the time, rate and extent of settlement of structures founded on fine-grained soils. It is also helpful in analyzing the stress history of soil. Since the settlement analysis of the foundation depends mainly on the values determined by the test, this test is very important for foundation design. The consolidation of soil is also very important in the case of highway embankments, especially where the height of embankment is more than 6 m high above the existing ground levels. Extra studies on consolidation are required in marshy areas, valleys, and high water table regions. Equipments and tools. Consolidometer with a loading device. Specimen ring. 2 porous plates or stones. Soil trimming tools. Dial gauge. Water content cans. Steel ball. Weighing balance. Electrical oven. Stopwatch. Principle involved. When a compressive load is applied to soil mass, a decrease in its volume takes place. The decrease in volume of soil mass under stress is known as compression, and the property of soil mass pertaining to its tendency to decrease in volume under pressure is known as compressibility. In a saturated soil mass having its void filled with incompressible water, decrease in volume or compression can take place when water is expelled out of the voids. Such a compression resulting from a long-time static load and the consequent escape of pore water is termed as consolidation. Then the load is applied on the saturated soil mass. The entire load is carried by pore water in the beginning. As the water starts escaping from the voids, the hydrostatic pressure in water gets gradually dissipated and the load is shifted to the soil solids, which increases effective on them. As a result, the soil mass decrease in volume. The rate of escape of water depends on the permeability of the soil. From the sample tube, eject the sample into the consolidation ring. The sample should project about 1 cm from outer ring. Trim the sample smooth and flush with top and bottom of the ring by using a knife. Clean the ring from outside and keep it ready from weighing. Remolded sample. Choose the density and water content at which samples has to be compacted from the moisture density relationship. Calculate the quantity of soil and water required to mix and compact. Compact the specimen in compaction mold in 3 layers using the standard rammers. Eject the specimen from the mold using the sample extractor. Test procedure. Saturate 2 porous stones either by boiling in distilled water about 15 minutes or by keeping them submerged in the distilled water for 4 to 8 hours. Wipe away excess water. Fittings of the consolidometer which is to be enclosed shall be moistened. Assemble the consolidometer, with the soil specimen and porous stones at top and bottom of specimen, providing a filter paper between the soil specimen and porous stone. Position the pressure pad centrally on the top porous stone. Mount the mold assembly on the loading frame, and center it such that the load applied is axial. Position the dial gauge to measure the vertical compression of the specimen. The dial gauge holder should be set in the beginning of its releases run, allowing sufficient margin for the swelling of the soil. Connect the mold assembly to the water reservoir and the sample is allowed to saturate. The level of the water in the reservoir should be at about the same level as the soil specimen. Apply an initial load to the assembly. The magnitude of this load should be chosen by trial, such that there is no swelling. It should be not less than 50 grams per centimeter square for ordinary soils and 25 grams per centimeter square for very soft soils. The load should be allowed to stand until there is no change in dial gauge readings for 2 consecutive hours or for a maximum of 24 hours. Note the final dial reading under the initial load. Apply first load of intensity 0.1 kilograms per centimeter square. Start the stopwatch simultaneously. Record the dial gauge readings at various time intervals. The dial gauge readings are taken until 90% consolidation is reached. Primary consolidation is gradually reached within 24 hours. At the end of the period specified above, take the dial reading and time reading. Double the load intensity and take the dial readings at various time intervals. Repeat this procedure for successive load increments. The usual loading intensity are as follows: 0.1, 0.2, 0.5, 1, 2, 4, and 8 kg per centimeter square. After the last loading is completed, reduce the load to of the value of the last load and allow it to stand for 24 hours. Reduce the load further in steps of the previous intensity till an intensity of 0.1 kilograms per centimeter square is reached. Take the final reading of the dial gauge. Reduce the load to the initial load, keep it for 24 hours and note the final readings of the dial gauge. Quickly dismantle the specimen assembly and remove the excess water on the soil specimen in oven. Note the dry weight of it. Observation and reading. Before performing test, dimensions are noted down and weights are calculated as applied load intensity, and take dial gauge readings for various intervals and repeat the procedure by changing load intensity, and the values are noted in table. Observation sheet for consolidation test, pressure voids ratio. After noting final dial gauge reading, specimen height and void ratio is calculated and noted in the table. Calculations. Height of solids is calculated from the equation HS equals weight of solids divided by specific gravity of soil into area. Void ratio. The voids ratio at the end of various pressures are calculated from equation E equals H minus HS divided by HS. Coefficient of consolidation. The coefficient of consolidation at each pressure's increment is calculated by using the following equations. CV equals 0.197 into D squared divided by T50, is known as log fitting method. CV equals 0.848 into D squared divided by T90, is known as square fitting method. In the log fitting method, a plot is made between dial reading and logarithmic of time. The time corresponding to 50% consolidation is determined. In the square root fitting method, a plot is made between dial readings and square root of time, and the time corresponding to 90% consolidation is determined. The values of CV are recorded in table. Compression index. To determine the compression index, a plot of voids ratio, E, versus log T is made. The initial compression curve would be a straight line and the slope of this line would give the compression index Cc. Coefficient of compressibility. It is calculated as follows. AV equals 0.435 into Cc divided by average pressure for the increment. Graph is drawn in between, voids ratio versus log sigma, average pressure for the increment. Coefficient of permeability, it is calculated as follows. K equals Cv into AV into unit weight of water, divided by 1 plus E.
Thank you for your time. If you have any queries, do not hesitate to contact us.